So welcome back. This is kind of our third session, lecture video on this topic of Thevenin's theorem. And what we're going to do is we'll start off just talking about what Thevenin's theorem is, and then we're going to do some circuit analysis and see how we can use it. So I prepared a sheet here. Thevenin's theorem, looking back from the load. So we have a circuit, let's say like this one here, and we have a load resistance, and we have some circuitry here. This happens to be a generator, but essentially we have a source somewhere back here, and you could even have multiple sources. We're going to learn a theorem that helps us take care of when there's more than one source in a circuit. Looking back from the load, and any sourcing circuit can be reduced to a voltage source in series with a resistance, or that could be an impedance. We mentioned that, and so I'll just keep that in there. We're just going to work on resistances to get the sense of this thing. And we do this in steps. The first thing is we disconnect the load. We deaden all the independent sources. And disconnecting the load, we'll just take the load resistor off, and we'll look back into the circuit. Look back into the circuit this way to see what we see. Looking back into the circuit from the load, which is disconnected. Well, let's fix that. So our load, which is disconnected, compute the resistance or impedance seen. This will be called R Thevenin or RTH, and if it were impedance, we'd call it ZTH. With the load still disconnected, compute the open circuit voltage, which is the voltage at the load terminals. Of course, the independent sources are no longer deadened. We've put them back in the circuit. The resulting open terminal voltage is called VTH, and we'll wind up with an equivalent circuit. Here's the VTH we computed, and here's the RTH or ZTH we've computed. So those are the steps. And so first I thought we'd take a look at this Thevenin's theorem example here, and we would just solve it as a regular circuit. So we have, using the total resistance method, we're going to look at what we've got from the source looking out. Okay, this is not the Thevenin's theorem method. First we're going to just solve this thing and get an answer. Then we'll go back and use Thevenin's theorem and see if we can get the same answer. So what we have here is we have R total is equal to R source. Right? We're going to have that in series with some other stuff here, and we're going to have R load in parallel with R3. That's going to be in series with R2, and that combination is going to be in parallel with R1. So we can say that we have R source, and that's going to be in series, and it's going to be added to R1 in parallel with, I'm sorry, my bad there. In parallel with the combination of R2 plus R3 in parallel with R load. So there's our total resistance. Now, if we look at this part right here, we have 150 ohms in parallel with 50 ohms, and I'm going to use product over the sum here, And I'm going to say that that's equal to 150 times 50 over 150 plus 50. Alright, and so what we're going to have here is we're going to have, that's going to be equal to 7,500, because 5 times 15 is 75, and we've got 2 zeros. 75 over 200, and that's going to give us 37.5 ohms. Okay. I'll try not to write any smaller than that. And so we have, we can rewrite our total. So our total is now equal to our source, which is 50 ohms, plus 150 ohms in parallel with 37.5 ohms plus 37.5 ohms. Well, this obviously is going to give us 75 ohms. And so now we have 75 in parallel with 150. So that's 150 times 75 divided by 225, and that is going to be equal to, we can actually do this by inspection. This is 150 is the same as 6 times 25, and 75 is the same as 3 times 25, and this particular guy down here is the same as 9 times 25, and so we can cancel out the 25s, and this is like 3 times 3, so we wind up with, essentially here, we wind up with, let's do it this way, 3 times 3 times 25, those will cancel out. We get 6 over 3 times 25, which is 2 times 25, which is 50 ohms. Another great thing you can do is just use your calculator and ignore all that junk. Alright? So now we have our total is equal to 50 ohms plus 50 ohms equals 100 ohms. Okay. Now, I should show the circuit. If we go back up here, we want to find this total current. That shouldn't be too hard. The total current is going to be equal to 12 volts. Well, it's going to be equal to total voltage divided by the total resistance, so it's going to be 12 volts divided by 100 ohms, which is going to equal 120 milliamperes, or 0.12 amps. And as you divide this by 100, you see your decimal point is going to go like that. You're going to get 0.12 amps. That's the same as 120 milliamps. Okay, well, with 120 milliamps, VR source is going to be equal to I total times R source, and it's going to be equal to, well, it's 6 volts, I'm sorry, it's 12, it's 120 MA times 50 ohms. We're going to wind up with and VR source will be equal to 6 volts. And with having lost 6 volts across, so I got 12 volts to start with, I'm going to lose 6 volts right here. I'm going to have V gen here is going to be equal to, so V gen is going to equal our source voltage minus VR source. Sorry, I got careless over here. VR source. And so we know that VR source is 6 volts, and so this is 12 volts minus 6 volts equals 6 volts. So now we have 6 volts across R1. So now I can go calculate the current through R1 is going to be equal to the voltage across R1 divided by R1, and the voltage across R1 is V gen. You just saw that, V gen from there to ground, if you will. And you know, we can certainly call this point ground if you like that. So V gen over 150 ohms, 6 volts divided by 150 ohms, and that's going to equal, well, let's see, 6 times 10 to the 0 volts divided by 1.5 times 10 to the 2 ohms. I'm going to do that in scientific instead of engineering. Either way is fine, and your calculator, I'm sure, will give a great result. Well, 1.5 goes into 6 4 times, so I'm going to get 4 times 10 to the 0 minus 2. In division, I subtract the exponents, and we get that IR1 is equal to 40 milliamperes. Sorry about that. Maybe I should show the things that I'm writing while I'm writing them. So once again, IR1 equals VR1 over R1, and VR1, as we can see, VR1 is the same thing as V gen. So V gen divided by 150 ohms, 6 volts over 150 ohms, that's 6 times 10 to the 0 volts divided by 1.5 times 10 to the 2 ohms. 4 times 10 to the 0 minus 2 is going to be 10 to the minus 2. That results in 40 milliamps. Okay, so now we have, we're going to have 40 milliamps going into here. We had 120 milliamps going into here, so the remaining 80 milliamps has to flow through R2. So we can use IR2 is going to be equal to I total minus IR1, and we get that by Kirchhoff's current law, because all the current flowing into this node right here, all the current flowing in has to equal all the current flowing out. And we know that 40 milliamps is flowing out, 120 in, so 80 milliamps has got to be flowing through R2. So we know here that IR2 is equal to 120 milliamps minus 40 milliamps equals 80 milliamps. And at that point, we can go back and look at R2 here. We know that 80 milliamps is flowing through here. We know what the voltage Vgen with respect to ground is. We can compute that voltage, and we can wind up with our load voltage here. And so if we want to compute our load voltage, well, what we can do is we can say that VR2 is equal to IR2 times R2. And that's going to be equal to that 40 milliamps, the 80 milliamps we computed times 37.5 ohms. I've just grabbed my calculator for that one. So we're going to have 80 milliamperes times 37.5 ohms is equal to, and let's bring up the old calculator here, and I'm going to clear that out. Hopefully we can get a decent focus on this. And I'm going to put 80 times 10 to the minus 3, because that's milliamps. 80 times 10 to the minus 3 times 37.5 ohms equals, and I get 3 volts. So, you think about it, 0.375 is 3/8. So 80 times 3/8 giving us a 3 kind of makes sense. So that gives us 3 volts. 80 times it, so that's 3 volts. And finally, we can say that V load is equal to, let's go back up here. We know Vgen is 6 volts. We know that this is 3 volts. So if the voltage from here to ground is 6 volts and I've got 3 volts here, the voltage from here to ground must also be 3 volts. So that 3 plus 3 equals 6. Alright, that's the Kirchhoff's voltage law. Just like we said that 12 volts, minus our total current times our source here, which gave us 6 volts. 12 volts minus 6 volts gave us 6 volts across here. Well, this 6 volts minus 80 milliamps times 37.5 gave us 3 volts here. So this 6 volts minus 3 volts gives us a remainder of 3 volts. So V load, and that's obviously also equal to VR3, is equal to Vgen minus VR2. V load equals VR3. They're the same voltage because they're in those two resistors, the load resistor and the R3 are in parallel. Is equal to Vgen minus VR2, and that's equal to 6 volts minus 3 volts equals 3 volts. Okay? And we'll push it one more time here. We know the load resistor is voltage is 3 volts, and it is 50 ohms. So let's figure out the current in the load. I load equals V load over R load. And so that's equal to 3 volts divided by 50 ohms. Now if that were 3 volts divided by 100 ohms, we'd have 30 mA, so I'm thinking this may be 60 milliamps here. Let's just bring in our friend the calculator, and we will say 3 volts divided by 50 ohms equals, and I get 60 times 10 to the minus 3, so that's 60 milliamps. So, sorry about that. So now I've got $60 milliamps down here, and I'm going to start another sheet. So what we figured out is that our load, there's our load voltage and there's our load current. Okay, 3 volts at 60 milliamps. Now let's go do this thing over again, and let's do this thing from a Thevenin theorem standpoint. And so we'll take the same circuit, and we've got our source 50 ohms. We've got a 12 volt sine wave here at 1 kilohertz, and we just treated that like a DC voltage before, because this is a resistive circuit, and so there's no delays. So we, our result here, go over in this other page, technically, if this is 12 volts peak here, then this is just 3 volts peak and 60 milliamps peak. Okay, or if it were RMS, we'll review what RMS means, but if it were RMS, we just write RMS for all those. But because it's a resistive circuit, we can treat everything as if it's a DC voltage. Okay, now we have our one here is 150 ohms. R2 is 37.5 ohms, and R3 is 150 ohms, and our load is 50 ohms. So let's apply our rules from Thevenin's theorem. First rule, we disconnect the load. So let's just say we look back here from the load, and we're going to do kind of a spooky thing here. We're going to this is the hairy eyeball looking back into our circuit like that. Okay, that is really horrible. Anyway, so we're looking back into our circuit like this, and so we're going to disconnect the load and look back this way. So we're going to pretend the load isn't even there. Then we're going to short out our power supply to deaden it. That's step 2. deaden all independent sources. We'll talk about what independent and dependent sources are as we go on in the semester, but everything we've talked about in the past have been independent sources. So what we do is we can just we can connect a short circuit right across there, and when we look back into here, what are we going to see? We're going to see our source in parallel with R1. So we're going to see this R Thevenin, we call it, is going to equal our source in parallel with R1. That's going to be in series with R2, and all of that's going to be in parallel with R3. If we look at what we computed in that last example, by the way, now this circuit's a bit of a cheat, because when we computed the total resistance, we're going to do some of these same calculations, all right? So I'm just going to say, when we look back at here, I'm going to have 50 ohms. This is product over the sum again, times 150 ohms divided by 50 ohms plus 150 ohms. And the last time we did this, we did 150 times 50 over 150 plus 50. We got 7,500 over 200, and that was 37.5 ohms. So this parallel combination here is going to equal 37.5 ohms. Okay. Now we're going to put that in series with R2, which is 37.5 ohms. All right, so if we want to take this a little farther, we've got 37.5 ohms plus 37.5 ohms, which gives us 75 ohms. And then we're going to put that in parallel with R3, which is 150 ohms. And when we did that previously, we put 150 in parallel with 75. We had 150 times 75 over 225, and it came out to be 50 ohms. And so when we do this again, we'll just do the same thing. 75 times 150 over 75 plus 150, that's 225. And this will be ohms, and that's going to be equal to 50 ohms. So you can see this kind of a special circuit. And I look back in, so R Thevenin equals 50 ohms. This circuit is designed for a 50 ohm system, and it's nice that it turns out that way. But now we have to calculate, so we now have, let's see what we've done with Thevenin's theorem. We disconnected the load, we deadened all sources. Looking back in, we found our Thevenin. Now we've got to find our load, our open circuit voltage with the load disconnected. I'm sorry. We have to find, with the load still disconnected, compute the open circuit voltage, which is the voltage at the load terminals. Of course, the independent sources are no longer deadened. The resulting open terminal voltage is called V Thevenin. So what we're going to have to do now is we're going to have to analyze our circuit And I'm just going to draw it one more time as this guy. And now when we come out to the load, we're just going to have open terminals out here because we have the load disconnected and we're trying to compute this open terminal voltage. And we'll put a ground here just for the heck of it. And this is 12 volts at 1 kilohertz. This is our source. It is 50 ohms. R1 is 150 ohms. R2, 37.5 ohms, and R3 is 150 ohms. And this is this is the voltage we're trying to find right here. This voltage is going to be our Thevenin voltage. It's the open circuit voltage. So we got to solve this with the total resistance method. So we'll say find open terminal, open circuit, open load, whatever you're going to call it, open terminal voltage. V Thevenin using the total resistance method. So in this case, V Thevenin is going to be equal to the voltage across R3. So we're really trying to find VR3. So let's do that. As we look from here, we know that R total is going to be equal to R source plus R1 is going to be in parallel with R2 plus R3. So what we basically got here, now R2 and R3, those will add up. Well, it looks like I'll have 187.5 ohms there. R1, of course, is 150, so what we're going to do in order to find this, we'll do a product over the sum. 150 times 187.5 over 150, plus 187.5, and we'll bring in our heavy number crunching equipment here. And so we have 150 times 187.5 divided by 150 plus 187.5. And it appears that we're going to get 83 1/3 ohms. So we'll kind of call it 83.3 ohms. And now we have to combine that with our source. So we can say that R total is equal to R source, which is 50 ohms, plus this combination here. You can call it R1, 2, 3 if you will, but it's 83.3 ohms, and obviously 8 and 5 is 13, so this is going to be a 133.3 ohms. And the next thing we want to find is I total, and that's going to be equal to V total divided by R total, and that's equal to 12 volts divided by 133.3 ohms. So we'll bring back this guy, and we will take 12 and we'll divide it by 133 point, that ought to be enough threes, don't you think? And we get right around 90 milliamps. So our total current, let's just call it 90 milliamperes. Okay. Alright, so looking at our circuit up here, we need to go from 12 volts down to this thing. I'm not going to call it VGen anymore because we don't have a load in the circuit, but we're going to have to get from 12 volts. We're going to lose some voltage across. Sorry, that's my tea mug in the way. So we're going to go from 12 volts. We're going to have a voltage drop across our source, and then we're going to have a voltage drop across this. Remember, this is like 83.3 ohms here, and that'll give us the voltage across R1. Okay, so let's do that. Let's take VR source, and let's see how much we're going to lose there. And that's going to be equal to I total, which is the same as IR source, or obviously, you know, times R source is going to be equal to 90 milliamps times 50 ohms. Okay, so if so let's bring in the calculator here, and we still have 90 milliamps on there, so let's multiply that by 50 ohms, and we get 4.5 volts. So this is going to give us 4.5 volts. All right. And now if we want to find the voltage across the load, we're going to have to look at a voltage divider application here. So VR, first of all, VR1, if you will, has got to be 12 volts minus the voltage across our source. So VR1 is equal to V total, I guess we've been calling it V source, whatever you want to call it, minus VR source. And that's Kirchhoff's voltage law again. Okay. And so what we have here is 12 volts minus 4.5 volts is going to be 7.5 volts. Obviously 7 and 4 is 11, and a half is 1, will give us 12 volts. So there's VR1. Oh man, I'm so sorry. There's VR1. It's equal to the total voltage, which is our 12 volts, minus the voltage across our source. By Kirchhoff's voltage law, that gives us the remaining voltage across R1, or across this. It's the same as the voltage across this whole combination here. and that's going to be 12 minus 4.5 is 7.5 volts. Now we can use our voltage divider rule. The 7.5 volts that appears here, okay, so we now know this guy's going to lose us 4.5 volts. And we know that this guy is 7.5 volts. So we now know from our voltage divider effect that we should be able to calculate the voltage at the load. So let's try to do that. In the voltage divider rule, now we can do this as a series circuit here with a current flowing and multiply the current times this resistor. The voltage divider rule does that very thing. It says that in this case, VR3 is going to equal VR3 is going to equal VR1, our total voltage, times R3 over R2 plus R3. There I go again. So VR3 equals VR1 times R3 over R2 plus R3, and what it says is that VR1, this VR1 right here, that's the voltage across this resistor. And the proportion of that voltage that's going to be across R3 is the same as R3's proportion of this total resistance right here. So R3 over R2 plus R3 is that proportion. You could also say that R2 plus R3 is this series resistance, and when you divide VR1 by R2 plus R3, you get the current that's flowing right here. Okay? You then take that current and you multiply it by R3 and you get VR3. So, no big secret in the voltage divider rule. Okay? And so, and we'll put a note here. We'll just say, you know, that this is called the voltage divider rule. And you can look it up. It's a thing, all right, as they say in the business. And so let's do some calculating here and see what we get. Before I bring that in, let's put our real numbers in here. VR3 is going to be equal to, we got VR1 is 7.5 volts times 150 ohms divided by 37.5 ohms plus 150 ohms. And let's do the business here. So I'm going to clear that off so that we have 7.5 times 150 divided by the quantity 37.5 plus 150, end of quantity. Okay? And survey says 6 volts. So this is 6 volts, and we can now say Thevenin equals 6 volts. So given that Thevenin equals 6 volts, and given that Thevenin equals 50 ohms, I guess we can put this on here. we can now say that our Thevenin equivalent circuit is 6 volts. I guess we're going to stay at 1 kilohertz. Obviously, that doesn't change. And so that's V Thevenin, and R Thevenin is going to be equal to 50 ohms. And that's kind of interesting, because if we were to tack on, let's put our load resistor out here. So if our load is 50 ohms, we're going to have 6 volts divided across two 50 ohm resistors. We're going to have 3 volts at 50 ohms. And if we look at if we go way back to the beginning of this lecture and look at our load voltage, we computed that we would get 3 volts. And so Thevenin's theorem gives us the same answer here, 3 volts. This would be obviously 3 volts, because I got 6 volts dropped across 2 equal resistors. There's got to be 3 volts across each. So there's our first application there's our first introduction to and application of Thevenin's theorem. And so we'll talk more about this as we go forward. Thanks for sticking through this whole thing. And we'll see you next time. Bye-bye.